Come on. Oh. Here's one. So a lot of the most interesting applications in this course are tied to the problem of eigenvectors, all right? So later we study these things called eigenvectors, which is like German for proper vector or something like that. And what these allow us to do is to decouple a problem. So a lot of problems that are linear, they come with all the variables kind of intertwined, so to speak, right? If you can find eigencoordinates, the variables kind of separate and the problem becomes easy to understand. So for example, this quadratic form, 4xy, right? What is that? Oh, we started late though. Right? Yeah, so I'm almost done though, don't worry. Anyway, so like 4xy is a quadratic form. And like, what is it? What is it? So if you calculate the matrix of this, you can find its eigenvalues. They turn out to be 2 and minus 2. And what that means is you can change to eigencoordinates where the formula for the quadratic form, instead of being this coupled thing, becomes uncoupled. It's just minus 2x bar squared plus 2y bar squared. You look at that, and you can tell immediately what this is. If you set this equal to a constant, those give you hyperbolas. Right? It's not an accident. The eigencoordinates for a symmetric real matrix correspond to actual rotations. So like 4xy equals to a constant is a rotated hyperbola. This is the proof of that. And that comes to you from a linear algebra calculation. So finding eigencoordinates can greatly simplify problems. Here's a picture of it for what it's worth. This is a picture of like a graph of z equals to 4xy. And the eigencoordinates are the ones that sort of go along the maximal drop off of the saddle or the maximum increase of the saddle. I think they're along the lines y equals plus or minus x in this case, for what it's worth. You stupid page up command. I hate you. Why did you do that to me, jerk? All right. Differential equations, right? Now, some of you may already know this, but if you want to solve like this set of differential equations, dx dt equals x minus 4y, dy dt equals minus 10x plus 19y, right? This, for example, could be something about tigers and rabbits, like tigers eating rabbits and rabbits out producing tigers or something. I don't know. You come to these kinds of problems from study of populations, growth and decline, and it's coupled, right? The number of tigers, the more tigers there are around to hunt buddies, the quicker they die, right? If there's no bunnies for the tigers to eat, that's also bad for the tigers. So whatever, you have this kind of problem. So it turns out that you can solve these problems, again, by finding eigenvectors. I'll describe how probably later. And so solutions to those sorts of differential equations come from linear algebra. Let me see if I can find my picture in here. Then I'll stop. Where's my picture? Here it is. So just to give you another example of decoupling. In the coordinates x and y, we have x prime is x plus y, and y prime is 3x minus y. This is a system of two differential equations and two unknowns. The change of x involves x and y. The change of y involves x and y. This is coupled, right? If I change coordinates, though, all right, well, this is the way we'll solve it, which is just like a standard technique, all right? You find the eigenvector, you write down this, bam, that's the solution. It's like a 10-minute problem. This is actually a nice test question, all right? The other way of looking at it, though, is to change variables to the eigencoordinates. And if you do that, you find these eigenvectors, you change to eigencoordinates. In the eigencoordinates, that differential equation just becomes dx bar dt equals to minus 2x bar, and dy bar dt equals to 2y. So now the change in x bar just involves x bar. The change in y bar just involves y bar. We've decoupled the problem using eigenvectors, actually eigencoordinates. And so you can solve these, separate, integrate, right? Just integrate e to the minus 2t, right? E to the plus 2t as your solutions. You can separate like Calc 2 style. You all like Calc 2, you know this. Maybe it's rusty, but you can do it. And you can see all of this going on. Here's a picture of the solution set. So these directions, which the solution gets kind of sucked into, those are actually the eigenvectors for the coefficient matrix for what we studied. So I guess what I'm trying to communicate to you is like the most exciting applications, in my view, for this course are all attached to eigenvectors. But this book has so much more. I've got a lot to learn from this book, and I hope that we can learn together. I won't be much ahead of you in here. I mean, I'm going to be learning this book with you guys. There's tons for me to learn in here. So I'm kind of excited about it. But anyway, thanks for your patience. Sorry for this class getting added to this very late date, but yep.
So, as far as like the course plan or syllabus for that coming like later,
We're going to follow the syllabus that Dr. Smith put out. So like I won't have homework for credit, but I will try to follow the book and suggest homework. And we can talk about suggested homework in here, of course. And I think he's got a couple of big projects he's planning. I'm probably just going to rip off his projects because he's thought about it a lot more than I have, and they're probably good. I have spent at least 2 minutes looking at his syllabus. But I mean, what I should do, of course, is to read the book, make sure that I can really commit to it. Because if it's too far away from who I am as an instructor, I might want to divorce myself from the book. I don't think this is going to happen, but every once in a while I'll read a book and it says something so offensive that I can't be part of it, you know? I don't see this book as being that book, but then again, let me spend a couple of hours in the book before I commit to it 100%, yeah? Yep.
If this section is happening, then do we have to drop and then react, or?
This I do not know. I'm going to go talk to Professor Young about what the procedure is next, yes. And we will email you what you should do. Absolutely. Yeah.
It continues to next week. I don't think we can.
Oh, no. This needs to be resolved,
yeah,
like,
now.
in the next day. Thanks, guys.